The cosmos holds its deepest truths just beyond our grasp. What if the universe's greatest secrets are not impenetrable mysteries, but intricate puzzles waiting for the perfect key? We are about to embark on a journey through 30 mind-bending theories that attempt to do just that, to crack the codes of cosmic enigmas from the nature of dark matter to the eerie silence of the Fermi paradox. By the end, you'll possess a new understanding of the most compelling ideas shaping our view of reality. We will explore why the fabric of space might be an illusion and whether our entire existence could be a sophisticated simulation. What cosmic question has always lingered in the back of your mind? Our universe appears suspiciously well arranged for our existence. The fundamental forces that govern reality, like gravity and the strong nuclear force, are balanced on a razor's edge. If gravity were even slightly stronger, the universe would have collapsed back on itself moments after the Big Bang. If it were slightly weaker, stars and galaxies would never have formed at all. This is the fine-tuning problem, a cosmic coincidence so precise it seems to suggest a deliberate setup. How do we explain this apparent perfection without invoking a designer? One compelling answer lies in the concept of the multiverse. This theory proposes that our universe is not the only one. Instead, it is just a single bubble in a vast, frothing cosmic ocean of universes, each with its own unique set of physical laws and constants. In most of these universes, the conditions are wildly inhospitable. Some might collapse instantly, others might be composed of nothing but radiation, and in many, matter itself never coalesces. We simply find ourselves in one of the rare Goldilocks universes where the numbers just happen to be right for life to emerge. There are several ways scientists imagine this multiverse could exist. One model, the inflationary multiverse, suggests that the rapid expansion of space in our early universe is not a unique event. Instead, different regions of space are constantly undergoing their own Big Bangs, endlessly spawning new pocket universes disconnected from our own. Another idea stems from the strange world of quantum mechanics, called the many worlds interpretation. Here, every time a quantum event has multiple possible outcomes, the entire universe splits, creating a new branch for each possibility. In this infinite branching tree of reality, every conceivable universe actually exists somewhere. So the reason our home seems so uniquely hospitable is not because it was chosen, but simply because we are here to observe it. In the cosmic lottery, we just happen to hold the winning ticket. But if the multiverse explains the fine-tuning of our reality, it leaves another, even larger cosmic puzzle completely untouched. What is the true nature of the invisible substance that holds our very galaxy together? We know it is there not because we can see it, but because we can watch its immense gravitational hand guiding the motion of stars. This is the enigma of dark matter. For decades, scientists have searched for a new, exotic particle to explain it, yet every experiment has come up empty. This repeated failure has opened the door for a radically different idea. Perhaps dark matter is not a sea of unknown particles at all, but a cosmic population of ancient, invisible objects. Primordial black holes. These are not the black holes formed from collapsing stars. They are thought to be relics from the universe's first frantic moments, when extreme densities could have squeezed lumps of matter directly into black holes. They could span a vast range of sizes, from as small as an asteroid to many times the mass of our Sun. Their primordial nature makes them perfect dark matter candidates. They are made of ordinary matter, just crushed into an ultra-dense state, so they would not interact with light or any other form of radiation. They would simply drift through the cosmos like ghostly icebergs in a dark sea, their gravity the only sign of their presence. We might be living in a galaxy filled with these ancient objects, their collective mass shaping the rotation of stars and providing the gravitational scaffolding for all cosmic structures. This theory even offers a tantalizing solution to another mystery. How did the supermassive black holes at the heart of galaxies grow so big so fast? Primordial black holes could be the missing seeds. Scattered throughout the early universe, they would have served as ready-made anchors for gas and dust to accumulate, jump-starting the growth of the colossal giants we observe today. Imagine a halo of these invisible primordial black holes surrounding our Milky Way. As they move, they would subtly warp the fabric of space around them, bending the light from distant stars in a telltale signature known as gravitational microlensing. Astronomers are actively searching for these fleeting distortions, hoping to catch a glimpse of the unseen architecture that holds our universe together. Gravity is not the only cosmic force with a hidden side. The very stage upon which the universe plays out, the smooth, continuous fabric of space and time, might itself be the ultimate illusion. This brings us to a theory so profound it challenges our most basic perception of reality. The holographic principle suggests that our universe, with its rich three-dimensional depth, is not the fundamental reality. Instead, it is a hologram, a magnificent projection from a vast two-dimensional surface that lies at the cosmic edge. Think of a credit card hologram, where a flat, patterned surface gives rise to a shimmering, three-dimensional image. The holographic principle proposes our entire cosmos operates on a similar, unimaginably vast scale. All the information that describes every star, every planet, and every one of us is actually encoded on a distant, two-dimensional boundary like a cosmic film. What we experience as reality is just a projection of that data. This radical idea did not emerge from pure philosophy, but from an intense struggle to understand the physics of black holes. Black holes present a deep paradox. According to Einstein's general relativity, anything that falls into a black hole is lost forever, its information seemingly erased from the universe. But quantum mechanics insists that information can never be truly destroyed. So where does the information go when it crosses the event horizon? The holographic principle offers an elegant, if bizarre, solution. The information is not lost inside the black hole. Instead, it is perfectly preserved, encoded on the two-dimensional surface of the event horizon itself. The three-dimensional space within the black hole is just a projection of that information. This resolves the paradox, suggesting information is never actually destroyed, merely translated. If this is true for black holes, could it be true for our entire universe? We might be living inside a colossal cosmic hologram. The world we see and feel, with its three spatial dimensions, would be an emergent property, a kind of illusion generated from a flat, two-dimensional shell at the edge of everything we can observe. This would mean that at the most fundamental level, the universe is not smooth and continuous, but pixelated, composed of tiny, indivisible units of information, much like the pixels on a screen. The apparent smoothness of space and time would be a consequence of these pixels being impossibly small. This theory forces us to reconsider the very nature of existence. What we perceive as the solid, tangible world may just be data flowing from a distant, flat surface, a shadow play on the wall of a deeper, simpler reality. But what if the cosmic ledger is not missing invisible matter, but is instead being read with the wrong set of rules? For decades, the hunt for dark matter has been a search for a ghost. Yet another theory proposes a far more fundamental revision, suggesting the ghost is not in the machine, but in our understanding of the machine itself. This is modified Newtonian dynamics, or MOND. Its premise is audacious that our grasp of gravity, the very force we thought we knew, is incomplete. The laws laid down by Newton and refined by Einstein work flawlessly in our solar system and in regions of strong gravity. But MOND proposes that in the extreme weak gravity found at the faint outskirts of galaxies, where the acceleration from gravity is incredibly tiny, the rules change. The force of gravity begins to behave differently, becoming stronger than expected. This single tweak to the cosmic formula aims to solve the dark matter problem not by adding matter, but by rewriting the script of gravity itself. The primary evidence for this radical idea comes from galactic rotation curves. According to Newtonian physics, stars on the outer edges of a spinning galaxy, far from the central mass, should move much more slowly than those near the center. Think of planets in our solar system, with distant Neptune plodding along compared to speedy Mercury. Yet when astronomers measure real galaxies, they find something astonishing. The outer stars race around at nearly the same speed as the inner ones, as if gripped by an unseen hand. MOND provides an elegant solution. It suggests that at these vast distances, the altered law of gravity gives those outer stars an extra tug, precisely accounting for their unexpected speed without needing any dark matter at all. For many individual galaxies, MOND predictions match the observed rotations with stunning accuracy, a success that has kept the theory alive and fiercely debated. However, the theory faces its own formidable challenges. While it beautifully explains the rotation of many isolated galaxies, it struggles with the immense gravitational pull observed in colossal galaxy clusters. These dense knots of thousands of galaxies seem to require more gravitational glue than MOND can easily provide, often forcing proponents to still invoke some form of unseen matter, undermining its core proposition. The cosmic tug-of-war between these two ideas, dark matter versus modified gravity, continues to define one of the greatest puzzles in modern physics. Are we surrounded by an invisible, dominant form of matter, or are we on the cusp of a revolution that will fundamentally rewrite our understanding of the universe's most familiar force? Perhaps the most intimate cosmic mystery is not written in the stars, but right here at home. How did life first spark on our young planet? The leap from sterile chemistry to a living, reproducing cell seems impossibly vast. But what if that monumental leap did not happen here at all? The theory of Panspermia proposes that the seeds of life are cosmic hitchhikers delivered to Earth from the depths of space. Our entire biosphere, from the smallest microbe to the largest whale, could be descended from interstellar travelers. This idea takes several forms. The most widely discussed is lithopanspermia, the notion that life can be transported between planets inside rocks. Imagine a massive asteroid impact on a life-bearing world like Mars, ejecting chunks of crust into space. These rocks become protective arcs, shielding any resilient microorganisms within from the harsh vacuum and radiation. After drifting for millions of years, one such fragment eventually crashes into the early Earth, delivering its precious cargo to a fertile new world. There is even a more speculative version called directed panspermia, which suggests this seeding was not a random act of celestial billiards, but a deliberate one. A technologically advanced civilization, perhaps seeking to spread life, could have intentionally sent microbial pioneers across the galaxy. While this remains firmly in the realm of speculation, the core idea of panspermia is supported by tangible evidence. Scientists have found amino acids, the fundamental building blocks of proteins, on certain types of meteorites. These are not life itself, but they are the complex organic Lego bricks from which life is constructed, proving that the essential ingredients for biology can form in the emptiness of space. Furthermore, we have discovered extremophiles, incredibly hardy microorganisms on Earth that thrive in conditions once thought uninhabitable, from boiling acid to frozen wastelands. Experiments on the International Space Station have shown that some of these organisms can survive for years in the vacuum of space, clinging to the outside of the station, enduring extreme temperature swings and punishing cosmic radiation. If life can be that tough, then surviving an interplanetary journey inside a rock seems entirely plausible. This theory profoundly reframes our search for life elsewhere. We may not be looking for independent origins on Mars or the ice-shrouded ocean moon Europa. We might instead be searching for our own long-lost relatives, descendants of the same cosmic seeding event. The entire solar system could be a single, interconnected ecosystem, its life shared across the void on comets and asteroids. Our own minds might hold the next great cosmic frontier. The mystery of consciousness, the raw subjective experience of being, remains one of science's most profound puzzles. How does the intricate electrical and chemical dance of a physical brain give rise to the feeling of awe, the color red, or a cherished memory? The quantum consciousness hypothesis proposes a radical answer, suggesting that the brain might be a quantum computer, and that the very nature of our awareness is rooted in the bizarre, probabilistic world of quantum mechanics. This theory attempts to bridge the chasm between the objective, physical brain and the intangible realm of subjective experience. It posits that phenomena like superposition, where a particle exists in multiple states at once, and entanglement, where particles remain mysteriously connected across vast distances, are not confined to the subatomic realm. They could be actively at work within the neural circuitry of our brains. The most famous model exploring this idea is the orchestrated objective reduction theory, or ORCH, proposed by physicist Roger Penrose and anesthesiologist Stuart Hameroff. They suggest that consciousness arises from quantum computations happening inside structures called microtubules, which are tiny protein scaffolds within our brain cells. In this view, these microtubules are the quantum processors of the mind. They could host quantum superpositions of neural states, essentially holding multiple potential thoughts or perceptions simultaneously. The collapse of this quantum wave function, a process Penrose links to the very fabric of spacetime, then selects one outcome, and this moment of selection is what we experience as a conscious thought. It is a breathtakingly ambitious idea, implying that our awareness is a direct dialogue between the cosmos and the quantum processes within our neurons. Yet, this theory faces immense skepticism. The primary challenge is the issue of decoherence. The warm, wet, and chaotic environment of the brain seems like the worst possible place for delicate quantum states to survive. Quantum effects are notoriously fragile, typically requiring extreme cold and isolation to be observed. Critics argue that any quantum superposition in the brain would be instantly destroyed by its noisy biological surroundings, collapsing far too quickly to play any meaningful role in conscious thought. For many neuroscientists, classical physics and complex neural networks are sufficient to explain brain function. Despite the controversy, the quantum consciousness hypothesis pushes us to consider a deeply interconnected universe. It raises the possibility that the mind is not merely a passive observer of the cosmos, but an active participant, its inner workings woven from the same fundamental threads that stitch together reality itself. What if our ability to ponder the stars is a direct consequence of the quantum laws that govern them? The very fabric of our reality might be a carefully crafted illusion. This is the simulation hypothesis, a theory proposing that our universe is not the foundational level of existence, but an incredibly advanced digital construct, not unlike a hyper-realistic video game. The laws of physics, in this view, are not fundamental truths but the underlying code of the simulation. The programmed rules that govern everything from the orbit of planets to the mysterious rules of quantum mechanics. Why would the universe be built on quantized, discrete packets of energy and information? Perhaps for the same reason a computer game uses pixels and bits for efficient processing. The sheer mathematical nature of our cosmos, how it can be so perfectly described by equations, could be interpreted as a signature of its programmed origins. The argument gains further traction when we consider the potential trajectory of our own civilization. If humanity continues to advance, we might one day create simulations so complex they contain sentient beings who believe their world is real. Now project that forward. Any sufficiently advanced civilization would likely run not one, but countless such simulations. If that is the case, the number of simulated realities would vastly outnumber the one base reality. Statistically, which one are we more likely to be in? The odds seem to favor us being in one of the innumerable simulations. The philosophical implications are staggering. If this is a simulation, our entire history, our memories, and our very sense of self could be data streams. The concept of free will becomes a profound question. Are our choices truly our own, or are they the output of a deterministic algorithm? Yet compelling counter-arguments exist. A simulation of this complexity would require unimaginable computational power. Would even an advanced civilization bother to simulate every single quark in every distant star? Or would they use shortcuts, rendering only what is observed, much like a video game only loads the graphics you can see? Some physicists suggest we might one day find evidence of these shortcuts in high-energy cosmic rays, tiny glitches in the matrix that reveal the pixelated resolution of reality. Whether a profound truth or a philosophical phantom, the simulation hypothesis forces a radical reassessment of our place in the cosmos. Are we cosmic beings on a physical journey, or are we simply characters in the most sophisticated story ever told? The Big Bang Theory presents a compelling origin story, yet it leaves some cosmic questions unanswered. Why does the universe appear so remarkably uniform in all directions, as if every region had once been in perfect thermal contact? This is the horizon problem, and why is the geometry of the cosmos so perfectly flat, balanced precariously between eternal expansion and catastrophic collapse? This is the flatness problem. The theory of cosmic inflation provides an elegant solution, proposing that the universe underwent a breathtaking growth spurt in its very first moments. An unimaginably short time after the Big Bang, a mysterious force took over. For a fleeting fraction of a second, the cosmos expanded faster than the speed of light itself, not by moving through space, but by stretching the very fabric of space-time. In this inflationary epoch, a subatomic speck of reality was blown up to a size larger than our entire observable universe. This explosive expansion ironed out any initial wrinkles, explaining the stunning uniformity we see in the cosmic microwave background. It also stretched the geometry of space to the perfectly flat configuration we measure today, much like blowing up a small, wrinkled balloon to a vast, smooth surface. The engine for this incredible event is thought to be a hypothetical field that permeated all of space, known as the inflaton field. As this field relaxed into its lowest energy state, it released a colossal amount of energy, driving the exponential expansion and eventually reheating the universe to create the hot soup of particles that would later form atoms, stars, and galaxies. But inflation did more than just smooth and flatten. It also planted the seeds for all future structure. On the smallest quantum scales, tiny fluctuations in the inflaton field were stretched to astronomical sizes during the rapid expansion. These minute variations in density became the gravitational seeds around which matter would later coalesce. Every galaxy, every cluster, and the vast cosmic web we observe today grew from those quantum ripples, magnified by inflation's incredible power. The entire large-scale architecture of our universe was thus imprinted in that first fleeting moment, a direct consequence of the microscopic tremors that shook the newborn cosmos. This profound silence from the cosmos is not just an absence of signals, it is a haunting question. Where is everybody? This is the Fermi paradox, the stark contradiction between the high probability of alien civilizations and our complete lack of evidence for them. One terrifyingly elegant answer is the Great Filter. This theory suggests that the evolution of life from its genesis to a galaxy-spanning civilization is not a smooth path. Somewhere along that cosmic timeline, there exists a barrier, a challenge so immense that it stops nearly every civilization in its tracks. The Great Filter is the reason the galaxy seems so empty, because almost no one makes it through. The crucial, unsettling question is whether this filter lies in our past or in our future. If the filter is behind us, we are cosmic anomalies. Perhaps the leap from simple chemistry to self-replicating life is astronomically rare, a fluke that happened only once in our solar system. Or maybe the transition from single-celled organisms to complex, multicellular life is the true bottleneck, a biological hurdle that took billions of years to clear on Earth and might be nearly impossible elsewhere. In this scenario, we are the first, the pioneers, lonely because we are the only ones to have come this far. But the more chilling possibility is that the great filter still lies ahead of us. The very technology that allows us to search the stars could be our undoing. Perhaps every civilization, upon reaching a certain technological maturity, inevitably discovers the means of its own destruction, whether through nuclear war, engineered pandemics, or a runaway artificial intelligence. The development of advanced technology might be a universal suicide pill, a threshold beyond which no society can pass. Another potential future filter is the ominous nature of any discovery that allows interstellar travel. The energy requirements and technologies needed for such journeys could be so inherently dangerous that civilizations accidentally annihilate themselves in the process of unlocking them. This is the grim lottery of cosmic evolution. We must hope that the filter is a rare event we have already survived, like the emergence of DNA or the rise of intelligence, and not a looming catastrophe that awaits us just around the corner. Our continued existence may depend on being one of the very few to navigate a challenge that has ended countless other worlds. The quest to unify the cosmos has long been split between two powerful but incompatible descriptions of reality. Einstein's general relativity paints a beautiful picture of gravity as the curvature of spacetime, perfectly predicting the dance of planets and the bending of light. Yet, on the subatomic scale, quantum mechanics reveals a chaotic, probabilistic world where forces are carried by particles and certainty dissolves. For decades, these two pillars of physics have refused to speak the same language, creating a fundamental schism at the heart of our understanding. String theory emerges as a bold contender to bridge this divide, proposing a single, elegant framework that could be the universe's ultimate operating manual. Its core idea is breathtakingly simple. What if the fundamental building blocks of nature are not zero-dimensional points, but unimaginably tiny, one-dimensional loops of energy or strings? These strings are so small that if an atom were scaled up to the size of our solar system, a single string would be no larger than a tree on Earth. The magic of this theory lies in the vibration of these strings. Just as a single violin string can produce different notes depending on how it is plucked, a fundamental string can vibrate in a vast array of distinct patterns or modes. One specific resonance might correspond to an electron, another to a quark, and still another to the photon, the particle of light. In this symphony of the cosmos, every particle and every force is simply a different note played on the same tiny loops of string. The music of these vibrations literally defines the properties of matter and energy. To make this mathematical symphony work, however, string theory demands a far more expansive stage than the 3 dimensions of space and 1 of time that we experience. The equations only find harmony in a universe with 10 or even 11 dimensions. This immediately raises a profound question: where are these extra dimensions? The theory suggests they are compactified, curled up into a space so infinitesimally small that they remain completely hidden from our perception. Imagine a garden hose seen from a great distance. It appears as a simple one-dimensional line. Only upon closer inspection do you discover its 2-dimensional surface, curled into a tiny cylinder. The extra dimensions of string theory are theorized to be curled into incredibly complex, 6-dimensional shapes known as Calabi-Yau manifolds. The specific geometry of this hidden landscape would determine the resonant patterns of the strings, which in turn would fix the constants of nature, like the mass of an electron or the strength of gravity. This leads to the concept of the string theory landscape, a vast, perhaps infinite, collection of possible vacuum states. each with its own unique Calabi-Yau geometry and its own resulting set of physical laws. Our universe, with its particular constants and forces, would then be just one possible bubble in a multiverse of physical realities, a single tune in an endless cosmic repertoire. While the mathematics is profoundly beautiful, string theory remains just that, a theory. Its energy scales are currently far beyond the reach of any conceivable particle accelerator, making direct experimental validation a monumental challenge. Yet, it stands as one of the most ambitious and comprehensive attempts to answer the ultimate question, to find a single, unified language that can describe everything from the birth of the cosmos to the quantum jitter of a single atom. Our orderly universe might be the ultimate statistical fluke. This is the deeply unsettling premise of the Boltzmann brain paradox, a thought experiment that pushes our understanding of reality to its breaking point. It begins with the second law of thermodynamics, which states that the universe as a whole trends toward disorder or higher entropy. A cup of hot coffee cools down, it never spontaneously heats up. A shattered glass does not reassemble itself, yet the law is statistical, not absolute. In a system that has reached maximum disorder, a state known as thermal equilibrium, random fluctuations can still occur. Given enough time, a random jostling of atoms could, by pure chance, arrange themselves into any configuration, no matter how orderly. Now, consider a cosmos that is either infinite in size or eternal in duration, or both. In such a vast and ancient arena, every possible fluctuation, no matter how improbable, is not just possible but inevitable. The spontaneous formation of a fully formed, conscious brain, complete with a lifetime of fabricated memories, becomes astronomically more likely than the gradual, organized evolution of an entire universe filled with galaxies, stars, and planets. This phantom observer is known as a Boltzmann brain. Picture a single, disembodied brain drifting in the absolute void. It has no body, no past, no external reality. Yet, in an instant, it flickers into existence with the perfect, intricate neural configuration that gives it the unshakable illusion of a life. It remembers a childhood, the feeling of sunlight, the faces of loved ones, and the curiosity that led it to ponder the cosmos. All of it is a phantom narrative, a cosmic accident born from a random dance of particles in an otherwise dead and empty cosmos. The paradox cuts to the core of scientific reasoning. Our entire methodology is based on the reliability of our observations. We trust that the world we see and remember is real. But if Boltzmann brains are not only possible but vastly more probable than real brains in a real universe, then we must confront a horrifying statistical likelihood. It is far more probable that you are a momentary Boltzmann brain, hallucinating a universe that does not exist, than that you are a genuine person in the complex, low-entropy cosmos you seem to inhabit. This creates a profound crisis for models of an eternal universe. If our standard cosmological picture leads to the conclusion that nearly all conscious experiences are these false, fluctuating phantoms, then that picture is likely flawed. The paradox therefore acts as a filter, suggesting that our universe cannot be eternal in the way some theories propose. Its beginning, the Big Bang, with its incredibly low entropy state, might not be a puzzle to solve, but the very thing that saves us from this existential madness, providing a definitive starting point that makes our ordered reality far more probable than a fleeting phantom in the void. While the paradox of the Boltzmann brain questions the very fabric of our reality, another cosmic concept offers a tangible, if theoretical, escape route from our own universe. Einstein's equations of general relativity, which so beautifully describe the warping of spacetime by gravity, contain solutions even more bizarre than black holes. They predict the existence of their perfect opposite, a white hole. If a black hole is a cosmic drain from which nothing can return, a white hole is a gushing fountain, an exit-only portal that violently expels matter and energy but allows nothing to enter. It is a one-way street out of reality. While no white hole has ever been observed, the mathematics suggests they could be the other end of the black hole tunnel. This is where the concept of the wormhole emerges, often called an Einstein-Rosen bridge. Imagine taking a sheet of paper and drawing two dots on opposite ends. The normal distance between them is the entire length of the page. But if you fold the paper so the dots touch, you have created a shortcut. A wormhole is that fold in the fabric of space-time, a tunnel connecting two distant points, or perhaps even two entirely separate universes. The entrance would be a black hole, the point of immense gravitational attraction, while the exit would be that erupting white hole, spewing the traveler out into a new region of space and time. This would not be faster than light travel in a local sense, but a cosmic cheat code, allowing a journey of billions of light years in the blink of an eye. The immense challenge, however, is that these theoretical tunnels are fantastically unstable. According to our current understanding, the moment even a single photon enters the wormhole, the tunnel would collapse into a singularity, snapping shut faster than information could pass through. To prop it open, to make it traversable, would require a substance that defies known physics, exotic matter. This is not merely antimatter, but a theoretical substance possessing negative energy density. It would have the bizarre property of repelling gravity rather than attracting it, acting as a kind of cosmic scaffolding to keep the wormhole's throat from crushing itself shut. The search for such exotic matter, or for a way to generate its effects, remains one of the most speculative frontiers of physics. Yet, the promise is so profound it fuels our imagination. A stable wormhole would be the ultimate gateway, a bridge not just across space, but potentially through time or into other dimensions, solving the mystery of cosmic connectivity on a grand scale. It offers a vision where the universe is not a vast, lonely expanse, but an intricate network of hidden passages waiting to be unlocked. The peaceful cosmic expansion we observe today might be a prelude to the most violent ending imaginable. While we currently think of dark energy as a gentle pressure accelerating the universe's growth, a more terrifying version could exist known as phantom energy. This hypothetical substance would not just push galaxies apart, it would turn the cosmos into its own executioner. The key difference lies in its behavior. If the density of phantom energy increases over time, its repulsive force would grow stronger and stronger without any limit. In this scenario, the expansion of space would not just accelerate, it would run away in an exponential frenzy, becoming infinitely powerful in a finite amount of time. The result is the Big Rip. First, the immense gravitational bonds holding galaxy clusters together would be overwhelmed. Galaxies would be flung into the ever-widening emptiness, isolated and alone. Then, the expansion would target individual galaxies. The Milky Way would be torn asunder, its stars scattered into the void like cosmic dust. Next, the violence would reach into our solar system. The phantom energy's grip would shatter the sun's hold on its planets. Earth would be ripped from its orbit, cast adrift in an ever colder darkness, but the destruction would not stop there. The force would then tear apart the planets themselves, and then the very atoms that constitute all matter. Protons and electrons would be pulled apart, and finally, the fabric of space-time itself would be shredded. The universe would end not with a collapse or a fade, but with a catastrophic rupture of reality's fundamental building blocks. This stands in stark contrast to other proposed endings. The Big Freeze, or heat death, sees the universe expanding forever but at a decelerating rate, gradually cooling into a dark, lifeless equilibrium where all energy is evenly distributed and no work can be done. The Big Crunch, on the other hand, is a dramatic reversal where gravity eventually wins, pulling all matter back together in a fiery collapse into a singularity, a mirror image of the Big Bang. The Big Rip is uniquely terrifying because it is an end from within, a fate dictated by the very vacuum of space turning against itself. It presents a cosmos that does not just cool or collapse, but actively self-destructs, leaving nothing behind, not even the atoms to tell its story. Perhaps our cosmic loneliness is not a symptom of our insignificance, but a mark of our value. The zoo hypothesis offers a serene, yet equally unsettling answer to the Fermi paradox. It proposes that advanced extraterrestrial civilizations are not absent, but are instead watching us from a distance, deliberately choosing to remain silent. In this view, Earth is a designated sanctuary, a cosmic wildlife preserve where humanity is the main exhibit. We are being left to evolve on our own terms, free from outside influence, our culture and technology developing along a natural, untainted path. The motivation for this galactic silence could be a form of universal ethics, a non-interference prime directive adhered to by all spacefaring societies. They might see contact as inherently destructive, a cultural shock that would irrevocably shatter our development, turning our unique trajectory into a mere echo of their own. Alternatively, their reason could be one of simple scientific curiosity. We are a living experiment, a study in how intelligent life emerges and grows when left entirely to its own devices. Or, in a more humbling scenario, they may just find us profoundly uninteresting, observing our global struggles with the detached fascination of a viewer watching an ant colony. This theory completely reframes our search for extraterrestrial intelligence, or SETI. Our efforts to listen for radio signals or beam out messages might be futile not because no one is there, but because the galactic community has collectively agreed to place our solar system under a kind of quarantine. Our signals might be intercepted and filtered out before they ever reach a wider audience, ensuring the preserve remains uncontaminated. This transforms our entire existence into a profound philosophical question. Are we the architects of our own destiny, or are we unwitting performers in a grand galactic theater, our every achievement and failure quietly documented by unseen patrons? The silence of the cosmos is no longer empty, but filled with the weight of infinite watching eyes. Our universe may not have a single definitive beginning or end. There are theories that paint a far grander picture where the cosmos is locked in an eternal, rhythmic dance of death and rebirth. This is the cyclic model, an idea that challenges the very notion of a singular Big Bang. Instead of a one-time creation event, the universe undergoes endless cycles. Each cycle begins with a Big Bang, expands for billions of years, and then, rather than fading into nothingness, contracts back in a cataclysmic Big Crunch. This collapse does not mark a final destruction, but a reset. The entire universe is compressed back into an ultra-hot, ultra-dense state, which then triggers the next Big Bang in an infinite, timeless loop. This cosmic heartbeat offers a stunning solution to the mystery of our universe's improbable low entropy at its start. The Big Bang is no longer a magical moment of perfect order appearing from nothing. Instead, the intense heat and energy of the Big Crunch effectively iron out all the wrinkles, wiping the cosmic slate clean and resetting the entropy clock for the next cycle. It is a universe perpetually renewing itself, a cosmic phoenix rising from its own ashes. Yet, another vision of cosmic cycles is even more radical. Roger Penrose's conformal cyclic cosmology proposes a cycle not of collapse and rebirth, but of infinite expansion and transformation. In this model, our universe is just one eon in an endless chain. The distant, cold future of one eon, where space is vast and empty and particles have lost all mass, becomes mathematically identical to the hot, dense, and smooth state of a new Big Bang. At the boundary between eons, the concept of scale and time loses all meaning. The impossibly large and stretched out becomes the impossibly small and condensed, and a new universe is born from the evaporated remains of the old. Penrose even suggests we might see the ghosts of previous eons imprinted on our own. He points to strange, circular patterns in the cosmic microwave background, which he interprets as the gravitational shockwaves of supermassive black hole collisions from the eon that came before ours. These theories transform our cosmic story from a single, fleeting performance into an epic with no final curtain. The question of our ultimate origin becomes a loop with no starting point, an infinite journey where every ending is merely a new beginning waiting to unfold. Far beyond the known planets, in the cold, dark reaches of our solar system, a ghost seems to be pulling the strings. Astronomers have detected a strange pattern in the distant Kuiper belt, a vast collection of icy debris left over from the solar system's formation. The orbits of a handful of these extremely remote objects are clustered together, all tilted in a similar direction and swooping around the Sun in a way that defies easy explanation. It is as if an unseen shepherd is herding them, guiding their paths with an immense gravitational hand. The most compelling theory for this celestial choreography is a hidden world, a true ninth planet of colossal proportions. This hypothetical planet 9 is not a small, rocky body like Pluto, but a super-Earth or a mini-Neptune with a mass up to 10 times that of our own world. Its gravitational influence would be powerful enough to sculpt the orbits of these distant Kuiper belt objects over billions of years, forcing them into their peculiar, clustered alignment. Scientists have even mapped its proposed path, a long, elliptical orbit that would take this frozen giant up to 20 times farther from the Sun than Neptune, completing a single journey around our star only once every 10 to 20,000 years. The hunt for this phantom planet is one of astronomy's great modern quests. Researchers are using some of the world's most powerful telescopes, like the Subaru telescope in Hawaii, to scan the vast celestial territory where it is predicted to be. They are looking for a single, faint point of light moving slowly against the background of fixed stars, a monumental task given the immense volume of space to search and the planet's expected dimness. Of course, not everyone is convinced a single massive object is the answer. Some propose that the collective gravity of many smaller, unseen Kuiper belt objects could, in theory, produce a similar shepherding effect. Others suggest our observational data is simply biased, that we have not found enough of these distant objects to see the true, random distribution of their orbits. Yet the Planet 9 hypothesis remains the most elegant solution, a tantalizing promise that a major world is still waiting to be discovered in our own cosmic neighborhood. Its discovery would not just be about adding a new planet to our charts, it would rewrite the story of our solar system's formation and evolution, revealing a dramatic, previously hidden chapter in our own backyard. The smooth, continuous stage of spacetime described by Einstein might be a grand illusion. To truly understand the universe's core, we must journey down to the smallest possible scales where gravity and quantum mechanics collide. This is the frontier of quantum gravity, a quest to find a single theory that can describe how gravity works in the realm of the fantastically tiny. One of the most compelling contenders is loop quantum gravity. This theory proposes a radical idea that space itself is not a smooth, featureless canvas. Instead, it is woven from a fabric of tiny, indivisible loops. Think of the fabric of your shirt. Up close, it is not a continuous sheet, it is a network of interwoven threads. Loop quantum gravity suggests spacetime is exactly like that, a dynamic web of a billion minuscule loops. These loops, or atoms of space, form a network of relationships, a spinning, vibrating structure that defines geometry itself. The theory paints a picture of reality as a vast, evolving spiderweb, where each connection carries a tiny bit of area and each intersection a tiny bit of volume. This concept of a granular spacetime has profound implications for the universe's most extreme environments. At the heart of a black hole, general relativity predicts a singularity, a point of infinite density where the laws of physics break down completely. But in loop quantum gravity, the fabric of space cannot be squeezed into an infinitely small point. There is a smallest possible size, a fundamental pixel of reality. This means the crushing collapse of a star does not end in a meaningless singularity, but rebounds at this minimum scale. The interior of a black hole could therefore be a bridge to another region of spacetime or even a new universe. This same logic revolutionizes our view of the Big Bang. The Standard Model describes it as the moment the universe erupted from an infinitely dense, infinitely hot singularity. But if space is quantized, there is no such thing as infinite density. The Big Bang was not the beginning of everything, but a great bounce. Our universe could have been born from the collapse of a previous cosmos, which contracted to a point of maximum density before quantum gravity effects caused it to rebound, igniting the expansion we see today. We can visualize this granular, quantized spacetime as a frothing, dynamic ocean of connections called a spin foam. Each bubble in this foam represents a quantum event, a possible history of how space itself evolves. This magnificent structure, a tapestry of a billion intertwined loops, might be the ultimate answer to what reality is made of, revealing that the universe is not a continuous stage, but a cosmic fabric woven from the threads of space and time themselves. This coherent stream of galaxy clusters moves with a purpose, as if pulled by a cosmic tide whose source lies beyond everything we can see. Astronomers call this phenomenon dark flow, and it presents a profound challenge to our standard model of the cosmos. According to our best understanding, the universe is expanding uniformly, with galaxies drifting apart in a stately, predictable dance. Yet, detailed studies of massive galaxy clusters reveal a different story. These immense structures are not just receding from us, they are also drifting sideways, all in the same direction, at velocities of over 2 million miles per hour. It is as if the entire observable universe is being subtly tugged toward a single point in the vast nothingness. What colossal force could possibly orchestrate such a motion? The most mind-bending explanation is that the gravitational source of this dark flow is not within our universe at all. It could be the pull of an immense concentration of matter that lies beyond our cosmological horizon, the ultimate edge of the observable universe. During the universe's initial inflationary period, space itself expanded faster than light, carrying entire regions of reality far beyond our ability to ever see or interact with them. But gravity, according to Einstein, is the curvature of spacetime itself. There is no fundamental reason why its influence should be limited by the speed of light or the reach of our telescopes. A supercluster of galaxies or a cosmic structure of unimaginable scale could be exerting its gravitational pull from this other domain, a ghostly hand reaching across the void to guide the motion of our local cosmos. This idea is, of course, deeply controversial. Skeptics suggest the dark flow signal could be an artifact of incomplete data or a subtle miscalibration in our instruments. The measurements are at the very limit of our technological capabilities, pushing the boundaries of what is detectable. Yet, if confirmed, the implications are staggering. Dark flow would be our first tangible, if indirect, evidence for the existence of something beyond our cosmic horizon. It would powerfully support the idea of a multiverse, suggesting that our universe is just one island in an infinite archipelago of realities, each with its own unique geography and content. We would be like sailors on a ship, feeling the pull of a distant, unseen continent, knowing that our map of the world was tragically incomplete. The mystery of dark flow compels us to ask what other unseen giants might be shaping our cosmic destiny from the shadows. Our own world might be a cosmic masterpiece of improbable perfection. The rare Earth hypothesis confronts the silence of the Fermi paradox, not with lurking observers or grim filters, but with a simple, profound idea. Perhaps intelligent, technological life is not an inevitable product of evolution, but an astronomically rare fluke, dependent on a long and precise chain of cosmic and planetary blessings. This theory suggests that while simple microbial life could be common throughout the galaxy, The leap to complex, intelligent beings requires a checklist of conditions so specific that Earth may be one of a handful of worlds to ever fulfill them all. Consider the sheer number of things that had to go right for us to be here. We orbit a stable, long-lived star, a G-type main sequence star that provides billions of years of steady, reliable energy. Many other stars are far more volatile, prone to violent flares that would routinely sterilize the surfaces of any orbiting planets. Our solar system itself is uniquely arranged for safety. A giant planet, Jupiter, acts as a gravitational shield, its immense bulk deflecting and capturing countless comets and asteroids that would otherwise bombard the inner planets with catastrophic frequency. Without this cosmic guardian, life on Earth would have faced constant extinction-level impacts, resetting the evolutionary clock again and again. Earth itself is a geological marvel. It has active plate tectonics, a process that acts as a global thermostat by recycling carbon and regulating our climate over eons. This constant churning of the crust also drives the formation of continents and recycles minerals essential for life, creating a dynamic and nutrient-rich environment. Then there is our oversized moon. The moon's gravitational pull stabilizes our planet's axial tilt, preventing wild, chaotic swings in climate that would render the surface uninhabitable for complex life. Without the moon, Earth might wobble like a spinning top, turning the poles tropical and the equator frozen in unpredictable cycles. Even our location in the galaxy is perfect. We reside in a quiet, habitable zone, far from the deadly radiation of the galactic core and its dense clusters of stars. Our position within the Milky Way's spiral arms provides a rich supply of heavier elements necessary for building planets and life. Yet we are sufficiently isolated to avoid frequent, disruptive close encounters with other star systems. Each of these factors is rare on its own, but their simultaneous occurrence on a single world for billions of uninterrupted years may be a near miracle. The universe could be teeming with bacterial slime and aquatic algae, but virtually empty of civilizations capable of looking back at the stars. We are not living in a zoo or facing a future filter. We may simply be the first and only ones to have won the ultimate cosmic lottery, living on a planet so perfectly tuned for complexity that its greatest achievement is the mind that now contemplates its own profound rarity. The serene darkness of a black hole's boundary may be a lethal illusion. We have long imagined the event horizon as a silent, invisible threshold, a point of no return where an astronaut would feel nothing unusual before being stretched into spaghetti by tidal forces. But this placid picture shatters upon a fundamental conflict between our two greatest theories of reality. Quantum mechanics insists that information, the specific identity of every particle, can never be erased from the universe. It can be scrambled but never destroyed. Yet, general relativity suggests that anything crossing the event horizon is lost forever, its information trapped within the black hole and seemingly erased when the black hole eventually evaporates via Hawking radiation. This is the information paradox, a direct contradiction that physicists have wrestled with for decades. One radical and deeply unsettling solution proposes that the event horizon is not a tranquil gateway but a seething inferno. This is the black hole firewall hypothesis. It suggests that to prevent information from being lost, a blazing wall of unimaginably high energy particles must exist just at the event horizon. Anything encountering this wall would be instantly vaporized, its information immediately scrambled and radiated back out into the universe, thus preserving the cosmic ledger. The object would not peacefully cross the horizon. It would be annihilated in a flash of pure energy. Imagine a starship pilot steering toward the dark silhouette of a black hole, only for the empty space before them to suddenly erupt into an incinerating barrier of fire, a cosmic shredder that protects the laws of physics by utterly destroying the traveler. This idea, while offering a solution to the paradox, has sparked a firestorm of its own in theoretical physics. critics argue it violates the core principle of general relativity, which states that an observer falling through the event horizon should experience no special, violent event, a concept known as the no-drama principle. You cannot have both no drama and a wall of fire. The two ideas are mutually exclusive. The firewall forces a brutal choice, demanding that one of our most trusted pillars of physics must break. Is Einstein's elegant picture of smooth spacetime wrong at the horizon, or is quantum mechanics' sacred rule about information flawed? The debate over this blazing boundary reveals just how little we truly understand about the most extreme environments in the cosmos, where the very laws of nature are pushed to their breaking point. Our own conscious observation might be the most critical instrument in unraveling the cosmos. This is the anthropic principle, a philosophical idea that places our existence at the very center of the cosmic fine-tuning mystery. It comes in two distinct forms, one a simple statement of fact, the other a far more profound and speculative claim. The weak anthropic principle is straightforward. It notes that we must find ourselves in a universe capable of sustaining life, because if it were not, we simply would not be here to ask the question. It is a cosmic version of the observation that a fish lives in water because it could not survive anywhere else. We observe a universe with precisely the right constants for life, not because it was designed for us, but because this is the only kind of universe in which observers like us could ever evolve. The laws of physics are not a question on a test with one correct answer. They are the environment we find ourselves in, and our presence is proof that this environment is habitable. The strong anthropic principle, however, takes a much bolder leap. It proposes that the universe, in some sense, must have properties that allow for the development of conscious life. This is not just a statistical observation, but a statement about the necessary character of reality itself. It suggests that the emergence of observers is a fundamental constraint on the universe's physical laws, as if the cosmos were built with the potential for mind already woven into its fabric. When paired with the multiverse theory, these principles find a powerful synergy. Within an infinite ensemble of universes, the weak anthropic principle explains our situation perfectly. We are not special, we are just fortunate, living in one of the rare bubbles where the numbers lined up. The strong version, however, might hint at a deeper connection. Perhaps the laws of physics are not random across the multiverse, but are somehow constrained or selected for their ability to produce complexity and consciousness. Picture a lone observer standing on a world, gazing out at a cosmos where every force, every constant, seems perfectly arranged to allow that very moment of contemplation. The stars are not just burning balls of gas, they are the furnaces that forged the heavy elements in their cores, the very atoms that now make up that observer's eyes and brain. The universe appears fine-tuned because it has produced the one thing that can recognize its own fine-tuned nature, us. This framing transforms our existence from a happy accident into the key that unlocks the cosmic coincidences. We are not just passive inhabitants of a random universe, but active participants whose presence is an integral part of its story. The anthropic principle, in its strongest form, challenges us to consider whether the universe could ever have been any other way, or if the potential for life and mind was written into its first moment, a silent promise waiting billions of years to be fulfilled. Deep in the Siberian wilderness, a century-old explosion remains one of Earth's most perplexing enigmas. On a June morning in 1908, a fireball brighter than the sun tore across the sky above the Tunguska River, culminating in a blast so powerful it flattened over 800 square miles of remote forest. The shockwave circled the globe twice, and for nights afterward, European skies glowed so brightly that people could read newspapers outdoors at midnight. The sheer force was thousands of times greater than the atomic bomb dropped on Hiroshima, yet when investigators finally reached the remote site decades later, they found no crater. The trees were scorched and knocked over in a vast radial pattern, pointing away from a central point of immense energy release, but the ground itself was eerily untouched. The absence of any impact crater has fueled endless speculation, with one of the most extraordinary theories suggesting the culprit was not a rock from space, but a needle of pure gravity, a primordial black hole. Imagine a tiny, incredibly dense black hole, perhaps no larger than an atom but with the mass of a large asteroid hurtling through the solar system. As it entered Earth's atmosphere at a tremendous speed, its immense gravity would have violently compressed and superheated the air in front of it. This process would have created a colossal shockwave and a fireball, effectively generating a titanic airburst just above the surface, perfectly explaining the widespread devastation without a crater. According to this wild idea, the black hole would not have stopped there. It would have sliced straight through our planet like a ghostly bullet, entering the atmosphere over Siberia, passing through the Earth's mantle and core, and exiting somewhere over the North Atlantic, all in less than a second. The energy released during its hypersonic passage through the atmosphere and rock would have been cataclysmic at the entry point, but the actual puncture through the planet would have been so clean and minuscule that it would leave no lasting geological trace for us to find. While a captivating solution to the missing crater, this theory faces a major hurdle, a complete lack of conclusive evidence. Scientists analyzing seismic records from that day found no unusual signals from the predicted exit point in the Atlantic. Furthermore, such a high-energy event punching through the planet should have left some detectable signature, perhaps a second atmospheric shockwave or a unique radiation signature, neither of which was ever reliably recorded. The mainstream scientific consensus still strongly favors a more conventional explanation, that a stony meteoroid or comet exploded in the atmosphere. But the primordial black hole theory endures as a fascinating, if fringe, possibility, a reminder that some of our planet's greatest mysteries might not be written in stone, but stitched into the very fabric of space-time, leaving scars we are only just beginning to perceive. That single, electrifying burst of radio noise remains etched in astronomical history as our most promising whisper from the cosmos. On August 15, 1977, the Big Ear Radio Telescope at Ohio State University was scanning the sky when it recorded a signal so powerful and so peculiar that the volunteer astronomer, Jerry Amon, famously circled the printed alphanumeric code in red pen and wrote "Wow!" beside it. The sequence 6EQUJ5 was not a message itself, but a scientific notation representing the signal's intensity over time. It lasted for a full 72 seconds, the exact duration the telescope's fixed horn could focus on a single point in the sky, and it screamed in on the hydrogen line, a frequency of 1,420 megahertz that scientists have long speculated would be a natural choice for interstellar communication. This is the frequency at which neutral hydrogen, the most abundant element in the universe, naturally emits light. Any civilization attempting to announce its presence might logically choose this universal channel, a cosmic hailing frequency. The WOW signal was not random static, it was a narrowband transmission, meaning all its energy was focused into a very specific, pure tone, just the kind of signature you would expect from an engineered beacon. Yet, after that one brilliant flash from the direction of the constellation Sagittarius, the signal vanished. Decades of subsequent searches targeting the same patch of sky have heard nothing but the usual cosmic background murmur. This profound silence is the heart of the mystery. If it was an alien beacon, why did it only flash once? The most compelling natural explanation points to a cosmic coincidence. Years after the signal was detected, astronomers proposed it could have been caused by hydrogen clouds surrounding a pair of passing comets that happened to be in that exact region of space at that exact time. The sun's radiation can make these cometary clouds glow brightly at the hydrogen line frequency, creating a temporary, strong radio source. It is a plausible, sobering solution. However, a meticulous review of the telescope's records revealed a critical flaw. The comets were not actually in the telescope's field of view on that fateful night. This theory, while elegant, collapsed under the weight of the evidence, leaving the door to the extraordinary once again wide open. So we are left with a haunting possibility. Did we briefly lock onto a celestial lighthouse, a beacon meant for someone else, or did we simply intercept a perfectly natural, one-in-a-billion astrophysical event that we still do not fully understand? The original printout with its red circled code is a permanent monument to that question, a single, tantalizing day to point in the vast and silent ocean of the cosmos. Sometimes the most profound cosmic mysteries are solved not by rewriting physics, but by accounting for a forgotten whisper of heat. For decades, two robotic pioneers, Pioneer 10 and Pioneer 11, presented scientists with a stubborn puzzle. As the spacecraft journeyed beyond the orbit of Pluto, traveling into the deep freeze of interstellar space, they began to slow down. It was an almost imperceptible deceleration, a tiny, persistent tug back toward the sun, a force equivalent to just 1/10,000,000th of the gravity we feel on Earth. Yet this pioneer anomaly was real, and it refused to go away. For years, it tantalized researchers with the possibility of new physics, perhaps a flaw in our understanding of gravity itself or the influence of some unseen, diffused dark matter halo. The solution, however, was far more mundane and in its own way brilliant. It came not from a grand new theory, but from a painstaking forensic investigation into the spacecraft themselves. The culprit was heat, but not from an external source. The pioneers were powered by radioactive plutonium, their electricity generated by the steady decay of this nuclear fuel. This process created warmth, which the spacecraft naturally radiated away into space as infrared light. The key insight was that this radiation was not perfectly even. The complex geometry of the probes meant more heat was emitted from the back, the side facing away from their direction of travel. Picture a car driving slowly on a cold night, its engine radiating warmth. Now imagine if the rear of that car glowed significantly hotter than the front. Each photon of infrared light carries a tiny amount of momentum, and as it streams away from the spacecraft, it gives a minuscule push in the opposite direction. With more heat photons pushing out from the back than from the front, the net effect was a tiny, continuous force acting as a brake, a gentle but constant pressure slowing the probes on their journey into the void. Unraveling this required heroic effort. Teams of scientists spent years recovering old telemetry data and building intricate thermal models of the decades-old spacecraft, accounting for every wire, every electronics box, and every patch of surface. They had to calculate precisely how much heat each component generated and, crucially, in which direction that heat was ultimately radiated into space. When they finally tallied it all up, the numbers aligned almost perfectly. The anomalous deceleration vanished, explained by the anisotropic, or directionally uneven, push of thermal radiation. This resolution is a powerful lesson in scientific humility. It shows that before we invoke dark matter or new laws of physics, we must first be certain we have accounted for every last glimmer of warmth, every subtle nudge from our own creations. The universe's secrets are often hidden not in the dramatic, but in the details we have overlooked. A strange, silent visitor tumbled through our inner solar system, and we almost missed it entirely. In October 2017, the Pan-STARRS telescope in Hawaii spotted an object moving at blistering speed, and trajectory so extreme it could only have come from beyond our solar system. This was Oumuamua, the first known interstellar visitor, and its peculiarities ignited a firestorm of debate. It exhibited no visible coma, the fuzzy envelope of gas and dust that typically surrounds comets, yet it was accelerating away from the sun in a way that gravity alone could not explain. This non-gravitational acceleration was the central mystery, a push from an unseen force. The most elegant solution paints a picture of a cosmic iceberg, but not one made of water. The leading natural theory suggests Oumuamua was a chunk of pure nitrogen ice, a fragment that likely broke off from a Pluto-like world in a distant star system. As this exotic iceberg neared the Sun, the intense heat would have caused the solid nitrogen on its surface to sublimate, transforming directly from a solid into a gas. This outgassing would have acted like a natural rocket engine, jetting invisible plumes of nitrogen vapor that gently pushed the object, explaining its unexpected acceleration. Because nitrogen gas is transparent and does not reflect sunlight like the dust and water vapor of a typical comet, this process would have occurred without creating a visible tail or coma, perfectly matching Oumuamua's stealthy behavior. The object's strange, flattened shape, initially described as cigar-like but later thought to be more pancake-shaped, also fits this model. A slab of nitrogen ice eroded unevenly by millennia of cosmic radiation, and its final close encounter with our star could easily have taken on such an unusual form. This theory elegantly connects the visitor to a known class of objects, as we see large plains of nitrogen ice right here in our solar system on Pluto and Triton. Contrast this with the more exotic proposal that Oumuamua was an artificial light sail, a piece of alien technology. While captivating, this idea rests on the absence of a natural explanation, a void that the nitrogen iceberg theory now fills with a plausible physical mechanism. The visitor's journey was a fleeting one, a single data point from the vast galactic ocean. Yet its legacy is a profound reminder that the universe is constantly sending us pieces of other worlds, fragments of distant planetary systems that carry their own unique stories, written not in language but in their composition and their silent, ghostly flight. Our cosmic blueprint, the faint afterglow of the Big Bang, might hold a subtle but shocking flaw. This is the mystery of the axis of evil, a name that perfectly captures the unnerving nature of the discovery within the cosmic microwave background. The CMB is the oldest light in the universe, a snapshot of the cosmos when it was just 380,000 years old, a time when it cooled enough for the first atoms to form and light to travel freely. This radiation bathes the entire sky, a nearly uniform sea of microwaves that reveals tiny temperature fluctuations, the seeds from which all galaxies and cosmic structures would eventually grow. According to our most fundamental cosmological principle, the universe should be isotropic, meaning it should look the same in every direction, with no preferred axis or special center. But when scientists mapped these subtle hot and cold spots in the CMB, they found something deeply strange. The largest scale fluctuations appear to be aligned along a particular axis, a kind of cosmic equator that seems to divide the sky. This alignment, this so-called axis of evil, suggests the universe might have a preferred direction, a spine around which its earliest structures are subtly organized. Imagine having a detailed map of the world, only to discover that all the continents are ever so slightly tilted, all pointing toward a single, invisible pole in space. That is the level of unease this cosmic axis creates. The most straightforward explanation is that this is simply a statistical fluke, a cosmic mirage created by the limitations of how we observe the sky. Perhaps our local motion through the universe, or even dust within our own galaxy, is creating a false signal that mimics this alignment. Yet, the anomaly has stubbornly persisted through multiple, increasingly precise satellite missions. If it is real, the implications are profound, forcing us to reconsider the very nature of cosmic inflation. The standard model of inflation was designed to create a smooth, isotropic universe, but perhaps the process was not perfectly uniform. More complex models suggest that the inflattened field, the engine of inflation, could have had a directional quality, stretching space slightly more in one direction than in others, imprinting a preferred axis onto the fabric of the newborn cosmos. Another, even more radical possibility is that this axis is a shadow of something beyond our observable universe, a gravitational tug from a colossal structure in the primordial multiverse that left its mark on our local cosmic bubble. The axis of evil remains one of cosmology's most tantalizing and controversial puzzles, a ghost in the machine of the Big Bang that challenges our most cherished assumptions about the universe's fundamental symmetry. High above our planet, a legend whispers through the void, a tale of an ancient alien sentinel silently watching us from the darkness. For decades, stories have swirled about the Black Knight satellite, a mysterious object of extraterrestrial origin said to be in a near-polar orbit around Earth. The truth, however, is a story not of alien visitors, but of human ingenuity, error, and the inevitable clutter we leave in our wake. The myth began to crystallize in the 1960s, fueled by a combination of genuine space events and creative misinterpretation. One of the primary culprits was the discarded cover from the United States Discoverer program, a series of early reconnaissance satellites. After deploying its secret payload, the large, reflective cover of the satellite was jettisoned into its own orbit. To observers on the ground, this tumbling, glinting object following an unusual path seemed like a perfect candidate for a mysterious craft. Then, in 1963, Major Gordon Cooper reported seeing a greenish object during his Mercury flight, a sighting later attributed to a faulty instrument panel and the high levels of carbon dioxide he was experiencing. The story was later amplified and woven into the Black Knight lore, creating a compelling but false narrative. The most iconic piece of evidence, a photograph of a strange, dark object against the Earth, is almost certainly a thermal blanket lost during a spacewalk from the space shuttle. These blankets are essential for temperature control, but if they become untethered, they drift away, taking on bizarre, angular shapes as they slowly tumble through the vacuum. When you place a photo of a lost thermal blanket side by side with the legendary Black Knight image, the resemblance is uncanny. The so-called alien craft bears all the hallmarks of a crinkled, human-made insulator, its dark surface and irregular form perfectly matching the object of so much speculation. The myth was further cemented by misinterpreted radio signals. In the 1920s, pioneering radio experimenters, including Nikola Tesla, detected strange, repeating signals that seemed to come from space. We now understand these were almost certainly natural phenomena, like whistlers caused by lightning interacting with the magnetosphere or the sounds of distant pulsars. At the time, with no context for such signals, it was easy to imagine an intelligent source. Over the years, these disparate threads, the lost debris, the astronaut sighting, and the mysterious signals, were all braided together into a single, compelling story of an alien artifact. The reality is far less dramatic, but no less a testament to our exploration. Our orbit is a graveyard of our own ambition, filled with discarded rocket bodies, dead satellites, and the occasional lost glove or tool. The Black Knight is not a silent watcher from another star, but a mirror reflecting our own activities back at us, a piece of space junk mistakenly crowned as a cosmic mystery. This resolution reminds us that before we look to the stars for answers, we must first understand the artifacts of our own journey, the mundane ghosts we have placed in the sky ourselves. Rising from the heart of our galaxy like two colossal, ghostly orbs, the Fermi bubbles are a breathtaking monument to a violent past. These vast structures, invisible to our eyes but glowing intensely in gamma-ray light, stretch for 25,000 light-years each, one bulging north of the galactic plane and the other south. Together, they form a titanic hourglass figure, a cosmic echo of a cataclysm that forever changed our galactic neighborhood. The leading theory points an accusing finger at the sleeping giant at the Milky Way's core, the supermassive black hole known as Sagittarius, a star. Though relatively quiet today, astronomers believe it awoke in a spectacular fury a few million years ago. In this ancient outburst, vast amounts of matter, drawn too close to the black hole's event horizon, were not swallowed whole. Instead, powerful magnetic fields funneled some of this superheated gas into two opposing jets, erupting from the black hole's poles at nearly the speed of light. These jets, acting like cosmic blowtorches, blasted their way out of the galactic center, inflating these gigantic bubbles of high-energy particles that we see today. Imagine the sheer force required to punch through the dense, gaseous disk of the galaxy, blowing a clear path for tens of thousands of light years and creating a cavity that still persists millions of years later. This event would have been the most brilliant beacon in the sky for any life forms on Earth at the time, a silent, searing flash from the constellation Sagittarius. Yet there is an alternative explanation for these colossal structures. Perhaps the bubbles were not forged by the black hole's rage, but by a frenzied burst of stellar birth. In this scenario, the galactic center experienced a period of intense star formation, where millions of stars were born in a relatively short cosmic time. The most massive of these stars would have lived fast and died young, exploding as supernova in a continuous rolling thunder of detonations. The combined energy from these countless stellar deaths could have blown a galactic superwind, a powerful outflow that also carved out the bubbles. This stellar fury, rather than a single black hole eruption, could be the sculptor of these gamma-ray ghosts. Determining the true architect is a primary goal of modern astronomy. By studying the precise composition and energy of the particles within the bubbles, scientists hope to find a chemical signature, a fingerprint that will conclusively point to either the violent jets of a feeding black hole or the collective fury of a million supernova. This ancient cataclysm, whether from a single monstrous entity or a chorus of stellar explosions, reveals that our galaxy is not a static, peaceful island. It is a dynamic and occasionally violent system, capable of events that reshape its very structure on a scale that dwarfs our entire solar system. The star KIC 8462852 refused to follow the rules. While most stars show gentle, rhythmic dips in brightness as planets pass in front of them, this one, nicknamed Tabby Star, plunged into darkness in chaotic, dramatic events. Its light would sometimes drop by a staggering 22%, a dimming so extreme it could not be caused by any ordinary planet. For a time, the most thrilling explanation was an alien megastructure, a vast swarm of energy-collecting panels known as a Dyson sphere under construction around the star. The dream of finding a civilization capable of such cosmic engineering captured our imagination. Yet the universe, as it often does, offered a more natural, if equally bizarre, solution. The key lay not in solid structures, but in fine, celestial dust. Astronomers discovered that the specific way the star dimmed held the answer. When a large, solid object like a planet transits a star, it blocks all wavelengths of light equally, creating a clean, uniform dip. But the dimming of Tabby's star was different. It was chromatic. The starlight dimmed more in blue wavelengths than in red. This is the classic signature of dust. Tiny dust grains, smaller than a particle of smoke, scatter and absorb blue light more effectively than red, letting the longer red wavelengths pass through more easily. Just like our sun appears red at sunset because dust in our atmosphere scatters the blue light away. The mystery was not a solid megastructure, but colossal, ragged clouds of this fine dust orbiting the star in a clumpy, uneven ring. Imagine a vast, lopsided swarm of fine powder, a cosmic debris field with dense clusters and empty voids, all on a wildly eccentric orbit. As these thick clouds of dust drifted between the star and our telescopes, they would cause the star's bizarre, irregular flickering and those deep, precipitous drops in brightness. Continued observation over years confirmed this dusty culprit. The star was seen dimming gradually over long periods, a slow fading consistent with a lingering, dispersed cloud of dust, and then brightening again as the cloud moved on. The final, compelling evidence came when astronomers caught the star in the act of dimming across the entire electromagnetic spectrum, from ultraviolet to infrared, with the most dramatic dimming occurring in the ultraviolet, exactly as a cloud of tiny particles would predict. The case for alien megastructures has largely dissolved, replaced by the picture of a young star, or perhaps a very old one, struggling through a violent and dusty phase of its life, possibly from the collision of comets or the breakup of a moon-sized body. The solution may be less thrilling than a galactic empire, but it reveals a universe rich with complex natural phenomena we are only just beginning to understand. Our cosmic inventory has long revealed a startling shortfall. After tallying all the stars, planets, and visible gas, we found that more than half of the ordinary matter in the universe was simply missing. This was not the elusive dark matter, but the normal stuff, the baryonic matter made of protons and neutrons that constitutes every star, every planet, and every one of us. For decades, this missing matter presented a profound embarrassment, a gap in our most basic accounting of the cosmos. The solution, it turns out, was hiding in the most immense and empty spaces imaginable, woven into the very architecture of the universe itself. This is the warm-hot intergalactic medium, or the WIM. Picture the cosmos not as a collection of isolated galaxies, but as a single, vast spiderweb. Galaxies are merely the dense knots where the threads intersect, but the true bulk of the structure is in the filaments themselves. The WIM is this cosmic web, a network of incredibly thin, superheated gas filaments that stretch for millions of light years between the galaxies. This gas is so tenuous, so incredibly diffuse, that a single cubic meter of it might contain only a few atoms, a vacuum far emptier than anything we can create in our best laboratories on Earth. Yet, when you sum up the sheer volume of these filaments, they contain more than enough mass to account for every last bit of the universe's missing ordinary matter. How do you see something that is practically invisible? The key lies in the brightest beacons in the universe, quasars. As the intense light from a distant quasar travels across the cosmos on its way to our telescopes, it passes through these faint filaments of the WIM. The gas, though sparse, is hot enough to be ionized, meaning its atoms have been stripped of their electrons. These free electrons can absorb specific, very high-energy wavelengths of the quasar's light, particularly in the far ultraviolet and soft X-ray part of the spectrum. It leaves a unique fingerprint, a series of tiny, telltale dips in the quasar's brilliant spectrum. By analyzing the pattern of these absorption lines, astronomers can not only confirm the WIM existence, but also measure its temperature, density, and chemical composition. This is how we take a census of the invisible, by watching the shadows it casts against the cosmic lights. Visualize the universe as a dark ocean with galaxies as islands. For years, we only saw the islands, but now we have discovered the warm, salty water that connects them all. A vast intergalactic sea that holds the final pieces of our own material origins. The discovery of the WIM completes our ledger of normal matter, confirming that the stuff we are made of did not vanish, but was simply hiding in plain sight, woven into the grand, luminous web of creation. We have traveled from the fine-tuned laws of our universe to the phantom tug of dark flow, from the possibility of ancient black holes to the illusion of a holographic reality. These 30 theories represent the cutting edge of human curiosity, a testament to our refusal to accept mystery as a final answer. Some ideas, like cosmic inflation, are pillars of modern cosmology, while others, like the simulation hypothesis, dwell at the farthest shores of speculation. Yet each one, in its own way, strives to pull back the cosmic curtain, to find a crack in the door of the unknown and peer through. The true power of science lies not in possessing all the answers, but in the relentless, brilliant pursuit of the questions themselves. It is this journey that transforms the terrifying void into a frontier of infinite possibility. So we turn this final question over to you. Which of these cosmic keys feels most like it could unlock the universe for you? Was it the chilling elegance of the great filter, the intimate dance of quantum consciousness, or the silent watch of the zoo hypothesis? What grand mystery calls to you from the darkness between the stars? Share your thoughts in the comments below, and if your curiosity is still burning, subscribe to continue this journey with us as we keep exploring the greatest secrets of the